briefly summarize what we did last time. So last time we did the direct comparison test, in which we are given a series that doesn't look as, that it's not going to look as simple as a geometric or as a p-series, but sort of behaves like those kind of series, you know, like those kind of simpler series. So the idea is to use end behavior analysis to come up with a simpler series that behaves the same way, and then use the direct comparison in the case that we obtain, or rather we compare with a convergent series, a simpler convergent series. Well, we need to show the inequality tiny, less than small, or in the case in which we compare with a simpler but divergent series, we need to actually show the inequality huge is greater than big, right? Now, in some cases, this test may fail in the case in which, even though we come up with a series that it's actually related, you know, or it's similar in end behavior, the test failed, like in this case in which we didn't get to compare that huge is greater than big, all right? So we, as a plan B, we have the limit comparison test, and again, we do the first part of the test. It's exactly the same. Come up with a new series that with similar behavior, and we need to determine whether it converges or diverges. However, we do not show an inequality, but we rather, in this case, set up a limit. In this case, that limit has to be positive and a finite number, and if those two conditions are met, well, then our original series does exactly whatever the test series does. So let's do another example. So we got sigma n equals 1 to infinity 7 to the n over 3 to the n plus 9n minus 3. Well, that one was the same series as at the beginning of the series, of the section in which we were describing what were we going to do about this section. So we need to, number one, compare this with so of course, I mean, in this case, using end behavior, we can neglect the lower order terms and just keep the higher order terms. Sigma n equals 1 to infinity 7 to the n over 3 to the n, which at the same time is n equals 1 to infinity 7/3 to the n power. And well, we need to describe this simpler series, and in this case, well, this looks like a r to the n, where the a in this case is the invisible one, r is 7/3, and well, the n power. So in this case, we have a divergent geometric series. Right? And well, it's divergent because if you observe the value of r, 7/3, that's the absolute value of 7/3 is greater than or equal to 1. That's why it's a divergent. So this is what we have to do in this case. Set up a limit. A sub n over b sub n as n approaches infinity, where in this case a sub n is always the original problem, the sequence related to the original problem, and b sub n the sequence related to the test series. Alright, so that's going to be a limit 7 to the n over 3 to the n plus 9n minus 3 over 7 to the n over 3 to the n. So n approaches infinity. And again, be sure to delimit the fraction so you know how to divide the fractions together. And again, dividing by a fraction, it's the same as multiplying by the reciprocal. So this is limit 7 to the n over 3 to the n plus 9n minus 3 times the reciprocal of this, which is 3 to the n over 7 to the n. Well, in this case, we can actually divide out the 7 to the n. And that in order to start simplifying the limit expression, so we can find a way to compute the final answer to to compute the limit actually. So this is limit 3 to the n over 3 to the n plus 9n minus 3 as n approaches infinity. And well, let me make this look like a product. So in this case, what do we have? So we have the same exponential factor, or the same exponential term in the numerator and denominator. And again, we can neglect all of this. So what we can do here is use the L'Hopital's rule actually 2 times. So that's one way to go about it. Another way to go about this limit is by dividing all terms by 3 over n. All right. However, if we go with the highest order term, so what do we have? This 3 to the n is being multiplied by an invisible one. And so this is multiplied by an invisible one. In this case, we can go about the ratio of the leading coefficients, which is 1 over 1. And the final answer to the limit is, in this case, 1. Now, is this limit positive? Is it finite? For this reason, sigma n equals 1 to infinity, 7 to the n over 3 to the n plus 9n minus 3 also, or rather diverges by limit comparison test, right? So we always have to state which test are we using, even if our work depicts actually the actual test, we always have to say divergence or convergence and clearly state which test it is. You can abbreviate, that's fine. For shorthand, it's fine, but we always have to state the test. And I think this concludes this section. So we may go about to what's it called? The next section, 11.5, which is the alternating series test. All right. So far, we have looked at series with positive terms only, like the geometric test, the geometric series test, well, in the case, for example, if we had a common ratio that it's a negative, well, we always had that absolute value to find the convergence or divergence of the series, but well, we really didn't compute, if you will, negative terms, so, or rather checked for this kind of series, which in this case are the alternating series. So what is the alternating series going to look like? Well, we already looked at that back when we look at sequences, when we had this alternating factor. This negative 1 to the n minus 1, that's what makes the terms of the series bounds between positive and negative, and that's not, yes? Yes, I put it last night. And that's not the only possibility. The other possibility is negative 1 to the n or negative 1 to the n plus 1. That's another way to express this kind of alternating factors, So that's what's going to make them a positive, negative, or sometimes negative, positive. Well, different ways to determine or to show an alternating series, right? Well, so there's a couple of conditions that have to be satisfied for an alternating series to converge. Number 1, the limit of the sequence related to the series has to converge to 0. If the limit is not 0 or infinity or DNE, whatever it is, then we stop there and we don't have to do anything else. And we also have to show that the sequence is decreasing. Why is that? Well, let me give you a brief picture of why do we want a decreasing sequence as opposed to an increasing sequence. Okay, so this is what happens with decreasing alternating series. So, for example, as an alternating sequence which first term is positive and then negative, then positive, then negative, positive, negative. But see the behavior, how it's actually converging to 0, for example, in this situation. So we want that decreasing behavior on the sequence, because otherwise in this case, if it's increasing, well, it starts at 0, well, it starts positive, negative, positive, negative. See how this gets big every time? It increases to infinity. It blows up to infinity. Yes, in an alternating fashion, but it blows up to either positive or negative. So that's why we want to make sure that this sequence defined by the series is decreasing. In that to ensure that this converges, right? This converges, well, in general to 0. It could be something else, all right? Well, so let's have a look at a couple of examples. So let's look at sigma n equals 1 to infinity, negative 1 to the n, 1 over n. So let's check for both conditions. So the first condition, does the sequence limit b sub n as n approaches infinity, is that equal to 0? Well, so is limit 1 over n. By the way, notice in this case how this b sub n right here in the limit does not include the alternating factor. All right, it's everything except the alternating factor. And so that's as n approaches infinity, and well, 1 over infinity, this is 0. So the first condition is satisfied. All right, let's check the second condition. The second condition is that b sub n plus 1 less than or equal b sub n. And well, what are we going to do? So wherever you see the letter n in your original sequence, replace with n plus 1. That's going to become 1 over n plus 1 less than or equal b sub n, which is the original sequence. Now, is that inequality true or false? It's true, right? Because 1 over n plus 1, that plus 1 is going to make the denominator smaller. I mean, the denominator bigger, and dividing by a bigger number, this will make a number smaller than 1 over n. So this inequality has to be true. And what do we have? Well, the two conditions have been satisfied. So the series converges by the alternating series test. I'm going to call it AST for short. All right, so converges because it satisfies both conditions. Let's look at another example. So for the next example, sigma n equals 1 to infinity, negative 1 to the n squared over n squared plus 5. So let's check the two conditions. So the first condition is the limit of b sub n as n approaches infinity equals to 0. In other words, is the limit of n squared over n squared plus 5 as n approaches infinity. Is that equal to 0? Well, what is this limit equal to? One. Well, this limit is 1, which is not 0, and so the first condition is not satisfied. So we can just, from here we can just say that it diverges by alternating series test. All right, and no need to bother check the other condition, because if one condition fails, why check the other? All right, so let's do what's next. All right, letter C, sigma n equals 2 to infinity cosine n pi. Well, so this series right here initially doesn't look like an alternating series, and But it is an alternating series in disguise actually, because, well, what happens with the cosine function? Isn't that a function that bounces between -1 and 1? Well, depending on what we have for the angle in here. Well, so let's look at this term, at this factor rather, in the numerator, cosine n pi. So cosine n pi, and starting at n equals to 2, that's going to be cosine up to pi, which equals, what's cosine up to pi? 1. What about cosine of 3 pi? 0. What about cosine of 4 pi? What is that? 1? It's -1, right? -1, and cosine 5 pi, 0, and then so the pattern continues 1, 0, -1. So this is how it bounces back and forth between -1 and 1. All right, and so this is what is going to happen here. Well, actually, no. I think this is 1, -1, 1, -1, right? I think that's how it bounces. And well, so we can express this summation, this series, the following way: sigma n equals 2 to infinity. That's -1 to some power over, or rather 1 over root of n. Okay, is -1 to the n going to be sufficient, or should we add 1 or subtract 1? Well, it starts at 2, so -1 to the second power, that's going to be a positive value, right? So that's going to be fine, -1 to the n. So let's check the first condition. The first condition is the limit b sub n approaches infinity, that is, limit 1 over the square root of n as n approaches infinity equal to 0. Well, in this case it is 0, right? 1 over a really big number is 0. The second condition, is this a decreasing sequence? Well, it's 1 over, or rather, b sub n plus 1. Is that less than or equal b sub n? Plus 1. Is that less than 0? So this inequality is true. So both conditions are satisfied, then converges by alternating series test. All right? Okay. So this is the first test in which we're going to look at something beyond just convergence. So as soon as we know that an alternating series converges, well, we can further discuss whether the series converges absolutely or whether it converges conditionally. So this is what we're going to do. So we're going to have a convergent alternating series. So we need to check that it converges, just regular convergence, if you will. Okay? And then what we're going to do is we're going to take the absolute value of the series, and we are going to create a whole new problem. It won't have anything to do with the alternating series. So in fact, we will have to forget about the alternating series. And then, if that new series converges, the new problem we create, then the original alternating series converges absolutely, because the absolute value of the series also converges. And in the second case, in which the new problem we create, we come up with a series that diverges, well, in this case, the series is said to converge conditionally, and it's conditioned only to converge by its alternating form, not, and in this case, not by its absolute value form. So that's why we call it absolute convergence versus conditional convergence. Okay, so this flow chart right here, it's going to help us. It's kind of a roadmap to follow when it comes to alternating series. So let's have a look at this flow chart. Number one, we're going to start with an alternating series, okay? And we need to check the two conditions. Number one, that the sequence related to the series converges to 0, and that the sequence is decreasing. If both conditions are satisfied, well, then we say that it converges, all right? But otherwise, if one of these two conditions fails, well, then diverges, and we're done. And we're done with the problem here. Now, once we find out that the series converges here, we have to further options right here, further ways. So number one, it converges absolutely if the series of the absolute value converges, but otherwise converges conditionally if the new series we obtain converges or rather diverges. So that's absolute convergence and conditional convergence, right? Okay, so let's have a look at this, at some examples checking for this absolute convergence. Okay, so we have another series, sigma n equals 1 to infinity of -1 to the n plus 1 over n squared plus 8. So number one, we have to check whether the series converges first, because if the series diverges, that is, if one of the conditions fails to be true, well, we're done, like the second example. So first condition, letter I, is the limit of the sequence b sub n as n approaches infinity equals to 0. In other words, limit n approaches infinity of 1 over n squared plus 8. What's that limit equal to? 0. Okay, first condition satisfied. Second condition, b sub n plus 1 less than or equal b sub n. In other words, the original sequence shifted by n plus 1, that is 1 over, I'm going to replace this n squared with n plus 1 squared plus 8. Is that less than or equal to 1 over n plus 8? Well, yes, because add 1 to the integer you plug it in here, and then square it on top of that. That's for sure going to make a denominator larger on the left-hand side of the inequality. And again, dividing by a larger number, that's going to give us a smaller number than on the right-hand side. Yeah?
Square plus 8?
Yes, n plus 1. So what we do is, every instance of n that we see in the sequence gets replaced with n plus 1.
The right side, the n squared.
Oh, yes, thank you. It's n squared. Oops, not this one. Thank you. N squared plus 8. All right, so the two conditions are satisfied. All right, so we're good to go. We're good to go to create a whole new problem. So let's go back to the flow chart. Number one, we managed to check that both conditions are satisfied. We're going to go to the convergence route right here. All right. Now from here we will determine whether the series will converge absolutely or just conditionally. That is, converges absolutely if the absolute value of the series converges, and converges conditionally if it diverges. That is, it's just conditioned to converge in its alternating form only. All right. And unfortunately not in its absolute value form. So this is what we do. Sigma n equals 1 to infinity, and take the absolute value of -1 to the n plus 1 over n squared plus 8. And well, so when we take the absolute value of the expression here, notice what's going to happen with this alternating factor. Well, that's to make that alternating factor disappear. Right? Because, I mean, that alternating factor, what does that do? That outputs a -1 and a +1, -1, +1, and if we take the absolute value of all those terms, every single term will become positive. So these absolute values, what they do is to cancel out that alternating factor. And well, let's forget about the alternating series. We're going to backtrack in its due time to the original alternating series. In the meantime, let's focus on this series. Well, let's use all the tools that we know so far about convergence and divergence of series. So number one, sigma n equals 1 to infinity, 1 over n squared plus 8. Well, for this one, I think we can use the comparison test, because if we observe the series, we can neglect the 8 and compare with sigma n equals 1 to infinity, 1 over n squared. And well, this series, which is a lot simpler than the one that we just obtained, this we know that is a convergent P-series. Alright, it's a convergent P-series. Well, so when it comes to comparison, so in this case, I think it's a lot easier to do the direct comparison than the limit comparison. So what I'm going to do here is, for convergence, we need to show that tiny is less than or equal to small. In other words, a sub n less than or equal b sub n. Which in this case, well, we've done this test a few times already. So a sub n is the original series, 1 over n squared plus 8, and b sub n is the one that we compare it with, 1 over n squared. Now, is this inequality true? Okay, it is true. So we managed to show that tiny is less than or equal to small. All right. So now let's backtrack to the original alternating series. So number one, because we managed to show tiny is less than or equal to small, this series converges by DCT, direct comparison test. And now, this is the series that we obtained by taking the absolute value of the series, because this whole new problem became a convergent series. Well, the original series, the alternating series, converges absolutely. It converges absolutely. All right. So, checking with our flowchart here. So again, we checked the two conditions for convergence. We got a convergent series. And then furthermore, we took the absolute value of the series and we found out that it was a convergent series. That whole new problem we created. So for this reason, the original alternating series will converge absolutely. Let's have a look at another example. So, letter B, sigma k equals 1 to infinity of -1 to the k, ln of k over k. So number one, let's check the conditions for convergence. So that is limit b sub n as, or rather in this case I should change to b sub k as k approaches infinity, because we're using letter k, you know. So that's limit ln of k over k as k approaches infinity. Well, let's compute this limit. And what we usually do is direct substitution. So for other limits, it was just really easy to just substitute the value, and we got a 0 in the end, all right? So, for example, in this case, if we use direct substitution, ln of infinity, that's infinity over infinity, so this is an indeterminate form. So this permits us to do any algebraic technique to compute this limit, and well, any factoring, any rationalizing a numerator or denominator, any, what else, multiplying by a conjugate, well, it doesn't seem like this limit is going to work with any of those algebraic techniques. However, in this case, we can do the L'Hopital's rule, which I'm going to abbreviate as LH, just for short, L'Hopital, just to indicate that we're going to use the L'Hopital's rule. And the way the L'Hopital's rule works is the derivative of the numerator divided by the derivative of the denominator. It's not the quotient rule. Not the quotient rule. So limit, so the derivative of ln of k, which is 1 over k, over the derivative of k, which is 1, as k approaches infinity. And rewriting this, it's going to give us limit of 1 over k as k approaches infinity. And well, in this case, the limit of 1 over k, well, that's 1 over infinity, which is 0. So the first condition is satisfied. The limit of the sequence converges to 0. All right? So for the second condition, so what do we have is this sequence, what's it called, decreasing sequence. So in other words is ln of k plus 1 divided by k plus 1. Is that less than or equal ln of k over k? Is this inequality true? Well, at the beginning it might be deceiving. Why would it be deceiving? Because what do we have in the numerator? An ln of k plus 1 versus some ln of k. But well, that k plus 1 is for sure larger than this case. And what do we have here? The opposite inequality sign, right? However, the denominator, which is a linear function, versus the numerator, which is a logarithmic function, the function in the denominator, which is a polynomial function, grows faster than the logarithmic function. And you can check that using a graph. You know, like, you can check the graph of ln of x, and you can check the graph of y equals x. So do you see how the polynomial function, in this case, well, the linear function grows faster or it's actually a bigger quantity for large values of n? All right. So for this reason, this is also true, and well, we can say that the series converges, the alternating series converges. So now, let's check for absolute convergence. So when it comes to absolute convergence, we're going to get the series, the original series, sigma n k equals 1 to infinity of the absolute value of negative 1 to the k, ln of k. And well, taking the absolute value of the expression eliminates the alternating factor. N equals 1 to infinity, ln of k over k. So we need to have a look at this whole new series. Forget about the alternating series for a few minutes. And well, let's find out a good test for this series. All right. Well, this is definitely not a geometric series because it's not of the form AR to the n. So we can actually discard that option. Number 2, is there another option for this? Maybe, well, P series. Direct P series is not. because we have that ln of k, and recall that the p series, it's only 1 over n to a power p, so it's not a direct p series in this case. What's next? Maybe, what else do we have? A comparison. So can we compare with something? All right, let's have a look. So compare with, I'm going to compare this series with n equals 1, sigma n equals 1 to infinity of 1 over n. Right? It has the look of 1 over n. All right. So in this case, this happens to be a divergent p series. Right? This is a divergent p series. All right. And well, so when it comes to direct comparison, and in the cases in which we have a divergent p series, we need to show that huge is greater than or equal to big. Not like the previous example in which we had to show that tiny is less than small. That's what we do when we compare with a simpler convergent series. But in this case, with a simpler divergent series, it has to be huge greater than big. That is, the original problem greater than or equal the test problem, well, the test series. Let's find out if that inequality is true for this case. So is ln of k over k greater than or equal 1 over k? Actually, I should use k here. All right. Is that inequality true? I mean, check the right-hand side of the inequality. It's always 1 regardless of the value of k. But in this case, ln of k, yes, even though the logarithmic function grows at a slower rate, well, it will for sure be bigger than 1 for large values of k. So this inequality is true. This new problem converges by direct comparison test, and here is where we now backtrack to the original alternating series. Oh yes, that's diverges. That's true. Thank you. Diverges by direct comparison. So in this case, the original series sigma n k equals 1 to infinity, negative 1 to the k, ln of k over k converges. Yes, it still converges, but it's not going to converge absolutely. It converges conditionally. Again, this series is only conditioned to converge only in its alternating form. In its absolute form, it's not going to converge because the absolute value of the series did not converge. It actually diverged, as opposed to the previous example in which, well, the original alternating series converges, and then the absolute value of that series gave us another convergent series. So that's why it converges absolutely, because it converges in its absolute form. Yes.
The future basis test, is it to show that diverges?
For this one?
Yes.
So yeah, we use the direct comparison test. So in this case, since we compare the absolute value of the series ln of k over k with 1 over k, which is a divergent p series. So for divergence, we need to show that huge is greater than big. And
so yeah, if you were to use convergent, it would be the
exactly, it would have been like in the previous example. So we compared with 1 over n squared, which is a convergent p series. In this case, we needed to show tiny less than small. It was true, converges, so the original series converge absolutely. All right. Okay.